The second derivative test for finding extrema. This test is going to help us find relative mins and maxes. So up here at the top, you guys can write down relative min and max. Relative min and relative max. So previous to this, it's been kind of cool because we've been able to find the first derivative, and then using the test intervals, we can find out if the original function was increasing or decreasing. And if it was increasing and then decreasing, we had a relative maximum. And if it was decreasing and then increasing, we had a relative minimum. That one is a little bit tedious because you have to go through finding the derivative and then finding the critical points and then plugging them into a test interval and then figuring out da-da-da-da-da. So the cool thing about the second derivative is that once you find out if it's concave up or concave down, you can immediately determine if it's a maximum or a minimum. For example, if you have a graph that's concave up, is that a minimum or a max? Minimum, because it has a point at the bottom. And if you have a graph that's concave down? Maximum, good, because you have the point up at the top. So the second derivative is going to help us find out if we have minimums and maximums as well. So right here it says second derivative test. It's used for finding the relative extrema, like we just talked about, as well as the points of inflection. It says let f be a function such that f prime of c equals 0. So the first derivative equals 0, and the second derivative exists on this open interval containing c. So there's these three rules that happen. The first one, if the second derivative, so if f double prime of c is greater than 0, or in other words, if the second derivative is positive, therefore f is what? What's the original function if the second derivative is positive? Good. Then f of c is concave up. And therefore, it has a relative minimum at c. So x equals c is a relative minimum. And I can draw a little picture that shows you that if this is what the original function looked like, that would be concave up, and it would have a relative minimum at that point c. The second one is just the opposite of this. So if the second derivative is negative, so if it's less than 0, then f of c is concave down, and it has a relative maximum. So f double prime of c is less than 0, then f of c is concave down, and x equals c is a relative max. And here's what that picture would look like. All right, so one's positive, one's negative. What's the only other option that it could be? 0, good. So if f double prime of c equals 0, that means that the test fails. So go ahead and underline that or highlight that. So the test fails, exclamation mark. And if that happens, then you have to go back to f prime and use f prime to figure out if it's a maximum or a minimum. So if this happens, use f prime of x, so just the first derivative of x, to test for max and min. Can somebody tell me why, if the second derivative test shows that the second derivative is equal to 0, why would that mean that the test fails? Yeah, kind of both of those things together. So essentially, if the second derivative is 0, it means that it has an inflection point right there. So you won't be able to tell if it's maximum or a minimum. So go back, or it's undefined. So go back to the first derivative to figure it out. So it's not telling you if it's concave up or down at that point. So that's why we can't know. So this second part, it says steps for using the second derivative test. So step 1 is you need to know the critical points of the first derivative. So find the critical numbers or the critical points by using f prime of x, the first derivative. The first derivative, the critical points of the first derivative are going to tell us, all right, that's where this first derivative equals 0. So that's going to tell us where the original function has a turning point or where it's undefined. So if we can find the critical points, we know that it has a turning point at one of those. Then we take the second derivative and we use the second derivative test to figure out if they're maximums or minimums. So we're going to test the concavity on those critical values. So test the concavity on those critical values. So if you find a critical point and the second derivative says that at that critical point it's positive, it means it's concave up, so it would have a minimum, and that critical point would be a minimum. Or vice versa, if you find a critical point and you test it in the second derivative and it's negative, it would mean that it's concave down, so it has to be a maximum at that point. All right, let's do this first example together. All right, so I know how much you guys love trigonometry. I want you guys to take a minute and I want you to go through and figure out what the first derivative of this is and find the critical points of the first derivative. So find the first derivative and set it equal to 0, and then find the critical points of that. All right, what's the derivative of 2 sine x? 2 cosine x. Hi, Jessica. That's okay. I'll get you a notes paper right now. Good. So the derivative of 2 sine x is 2 cosine x. So I'm going to write 2 cosine x for that first one. Here you go. All right, and what's the derivative of cosine of 2x?
Negative 2 sine of 2x.
Good, it's negative sine of 2x times 2 because of the chain rule. So you have to multiply times that 2 on the inside. So it's negative 2, if I can just compile this really quick. Negative 2 sine of 2x. So are we good there on the derivative?
Yeah.
All right, from here, if you set this equal to 0, you won't be able to solve it yet because you can't solve something that has cosines and sines in it. So we have to figure out a way to get all either factors, because right now these are different terms. The 2 cosine x and the sine are terms, so you can't really set that equal to 0 very easily. So in other words, we need to get factors. So this sine of 2x, what's one of the identities we can use?
2 sine of x cosine.
Good, so let me just write a little note. There's one of the trigonometric identities that says that sine of 2x equals 2 sine x cosine x. So we're going to use that identity. So 2 sine x cosine x is what we're going to be using. And so when we put this back into the function, we get that f prime of x equals 2 cosine x minus the 2 times the 2 gives me 4. Are you guys okay with that? Yeah. All right, and then sine x cosine x. So that's me replacing that little rule in there. All right, what do both of these terms have in common? They both have a 2 cosine x, so I'm going to get rid of that by factoring it out. So 2 cosine x times, what's left from the first term? 1, and then from the second term I have 2 sine of x. So now I can set that equal to 0, and it's much, much easier to solve because you can set each of the factors equal to 0 individually. So if I set 2 cosine x equal to 0, and if I set 1 minus 2 sine of x equal to 0, I want you guys to go ahead and take a minute and figure out what values of x would make these two things equal to 0. I'll give you a hint. There are 4 values in our range from 0 to 2 pi. So figure out what the 4 values are. So if you look at this unit circle that I've drawn here, so for cosine, if we divide by this 2 over here with cosine, I can get rid of that 2 and I just have cosine of x equals 0. So to figure out where cosine of x equals 0, where does cosine equal 0?
Pi over 2, 2 pi over 2.
Good, pi over 2 and 3 pi over 2, and those are both in my interval from 0 to 2 pi. So those are my 2 values that would make cosine equal to 0. And then for the second one, if I subtract 1 over to the other side and divide by negative 2, I get that sine of x equals 1/2. So where does sine equal 1/2? Pi over 6 and 5 pi over 6. That's perfect. All right, good.
Why aren't they negative for the cosine x? Why aren't they also negative 2?
They're not also negative 2 because if you look up here at our interval that we're looking at, we're only looking from 0 to 2 pi, so we don't include any of the negative values. Good question. All right, so from here, if you look back at the steps to test for that concavity thing, the first one was to find the first derivative and use it to find the critical points, so that's what we just did. What was the second step? Good, use the second derivative to find the concavity at these points. So now we have to take the second derivative and we have to see if the concavity is positive or negative at each of these 4 points. If it's positive, is it a min or a max? Good, it would be a min. So if it's positive, it's a min, and if it's negative, it's concave down, so it would be a max. So go back and do this now. So using the second derivative that we found, go back and find the derivative again. Sorry, we only found the first one. So go back and find the second derivative now. So you're going to be using this. That's the first derivative. Take the derivative of that one more time to find the second derivative. All right, so the derivative of this function again, so the second derivative of x should be negative 2 sine of x minus 4 cosine of 2x. You guys got that? Yeah. All right, cool. So now we have to evaluate. So we found the second derivative. Now we have to evaluate each of these critical points that I have listed over here on the left-hand side and plug them into the second derivative. And once again, if it's positive, then it's concave up, so it's a minimum. If it's negative, then it's concave down, so it's a maximum. So let's do the first one together, and then you guys can do the rest of them on your own. So for f double prime, here I'll write this in a different color so you guys can see that it's differentiated from up above. So f double prime of pi over 2, let's do that one first. That equals negative 2 sine of pi over 2 minus 4 cosine of 2 times pi over 2. All right, so for this first one, sine of pi over 2. So if I look over here and I go to pi over 2, what's the sine value at pi over 2? 1. So I go straight up and my sine value is 1. So I'm going to say that this is negative 2 times 1. And for the second term, I have negative 4 cosine, and then what happens to that 2 times pi over 2? Good, it just turns into a pi, so my 2's are going to cancel, so I have negative 4 times cosine of pi. So if I look over here, this is the point negative 1 comma 0. So what is cosine of pi? Negative 1, good. So negative 2 times 1 is negative 2, negative 4 times negative 1 is positive 4, so when I simplify this I get 2. Is that positive or negative? Positive. Positive, so that means that this is concave up, like a cup. So concave up, all right, means that it's a minimum or a maximum? Minimum, good, because there's a point at the bottom of that little smiley face. So if it's a minimum, that means that pi over 2 is a minimum. Now technically, it says use the second derivative to find the relative extrema. It's not super specific on whether or not they just want the x values or if they want the x and the y value, the actual point. So for today's sake, let's just do it the simpler way and just say that pi over 2 is a minimum. X equals pi over 2 is a minimum. If you were working on this on the AP test, I might say that if you were unsure, just be safe and go back and plug it into the original function, because if they did want both the x and the y, you should make sure to have it, and if they didn't, then they're not going to mark you wrong for putting the y answer as well. Alright, so we know that x equals pi over 2 is a minimum because it was concave up since it was positive. I want you guys to take a few minutes and go back and check 3 pi over 2, check pi over 6, and check 5 pi over 6 to figure out if those are positive or negative for their concavity, to figure out if they're minimums or maximums. Alright, so when you're done, you guys can check your answers. I have them written down right here. So we already went over that the second derivative of pi over 2 was concave up because it was positive, so it was a relative minimum. I also got the same thing for 3 pi over 2, that it was also concave up because it was positive 6, so it's a relative minimum as well. F double prime of pi over 6 I got was negative 3, so that's concave down, which is a relative maximum. And F double prime of 5 pi over 6 I got was negative 3, so concave down, which is also a relative maximum. Do any of you guys want to see any of these worked out? Alright, if you guys have questions about them, you guys can ask me again later. If you didn't finish, that's okay, we can finish again later. I just want to kind of get through the other two so we can be done for today. Alright, so let's look at the other side of the notes. So, number 2. Like I said, we got the hardest one done first. So we'll go to some of the easier ones now. Alright, this one. It says use the second derivative to find the relative extrema of this function. So again, we're going to do the same process as we did last time where we find the first derivative and we use the first derivative to find the critical points. So go ahead and do that now. When you're done finding those critical points, go ahead and find the second derivative and plug those critical points into the second derivative to figure out if the graph is concave up or down at those points to figure out if it's a maximum or a minimum. So I'll give you guys a few minutes to do this. Go ahead and do that. All right, so for this one, when you're finding the first derivative, what's the derivative of x? 1, and then the derivative of the square root of 1 minus x, which is 1 minus x to the 1/2, should be 1/2 times 1 minus x to the negative 1/2 times negative 1. Good, because of the chain rule. So when I simplify this a little bit, because I want to simplify it one more time just so I can write it neatly, I have 1 minus 1/2 times 1 minus x to the negative 1/2. So I want to set that equal to 0, and I want to solve for my critical points. So that's my first step for testing the relative maximum and relative minimums. So I'm going to subtract 1 over to the other side. So that's negative 1 on the other side, and I'm going to divide by that negative 1/2. So I get that 1 minus x to the negative 1/2 power should equal a positive 2. Do you guys get that? Yeah. All right. If I rewrite this 1 minus x to the negative 1/2 power, I can write 1 over 1 minus x to the 1/2 power equals 2. Now, in order for this to equal 2, I have 1 on the top and some number on the bottom, depending on what x is. In order for this to equal 2, that bottom has to equal 1/2, because 1 divided by 1/2 would be 2. So that's the only way that this can equal 2. Another way to show that is if you cross multiply. So if you multiply the 1 minus x to the 1/2 times 2 and then divide both sides by 2, it would still be 1/2. So I'm going to write that 1 minus x to the 1/2 should equal 1/2. So how do you get rid of something that's being square rooted to the power of 1/2? Square it. So I'm going to square both sides. So if I square both sides, I get 1 minus x on this side. Oops. 1 minus x on this side. And then 1/2 squared would be 1/4. And then if I subtract 1 from that, I get negative 3/4. And then divide by that negative, so I get a positive 3/4. So that is my critical point, at positive 3/4. Raise your hand if you got that. Positive 3/4. All right, good. A couple of you guys. Do you understand how to do it now? Yeah. All right, good. So what do we do after we find the critical point? The critical point is where the graph is turning. Now we have to figure out if it's a relative maximum or relative minimum. How do we do that? Good. Find the second derivative and plug it into that. So I'm going to use this equation here as my first derivative, and I want you to take the derivative of that one more time and figure out, when you plug in 3/4, if that second derivative is positive or negative. So what's the derivative of that 1? 0. So I have negative, so that goes to 0, so I'm just going to get rid of that. The negative 1/2 kind of tags along for the ride, so that's negative 1/2 that tags along for the ride. The derivative of 1 minus x to the negative 1/2 is negative 1/2 times 1 minus x to the negative 3/2 times negative 1 from the chain rule. So when I simplify that, I get positive 1/4, but then that negative 1 from the back comes back again and makes it negative. So that'd be negative 1/4 times 1 minus x to the negative 3/2. So I found the second derivative. Now the only thing left to do is to evaluate whether or not 3/4, x equals 3/4, this value we found here for our critical point. We need to evaluate if that makes the second derivative positive or negative. So I'm going to say f double prime of 3/4 equals negative 1/4 times 1 minus 3/4 to the negative 3/2. All right, 1 minus 3/4, that's 1/4. Is that term going to be positive or negative? 1/4 to the negative 3/2. The final thing will be negative because of the negative 1/4, but just this term here, let me highlight it in yellow so you guys can see it a little bit better. Just this term here is actually going to be positive because 1/4 to the negative 3/2, there's no way that's going to be negative because negative power or the negative exponent just makes it go under its own reciprocal. So that part won't be negative, but the negative 1/4 at the beginning will make it negative. So the answer is negative. So I don't even care what the number is as long as I know that it's negative, which means that the original function is concave. If it's negative, it's concave down. So because it's concave down, it means that it has a maximum a relative maximum at x equals 3/4. Again, I just found the x value. It would be pretty easy to plug that back into the original function to find the y value, but we won't do it right now. All right, let's look at number 3. Any questions on that one, by the way, before we move on? So it's the same process over and over again. Find the critical points, plug it in, check to see if it's positive or negative, so on and so forth. All right, let's look at number 3. This one, it might be helpful to look at that chart that we drew yesterday in our notes. So if you guys want to go ahead and look at that, that would be helpful. It says, using the graph below, what are the x coordinates of the inflection points of f? And notice that this is a graph of the second derivative. So it says y equals double prime of f. So the second derivative of f. So we're looking for what are the x coordinates of the inflection points of f. So look at your chart. Let me take a picture of somebody's chart so I can see if I can put it up here. Who has neat handwriting? Here we go. You have neatish handwriting. I love it. All right, let's see. I've never done this before. From camera. Oh my gosh, I gotta take this off so I can actually see the picture. All right, use photo. What? It's not even working? Done. All right. Okay, so essentially, this is the chart that Mediha drew. So I'm trying to find, the question is saying, at what x values does the original function have an inflection point? So if you look over here, we drew inflection point right over here. Do you guys see that? So what does f double prime have to do with inflection point? What do you guys notice is at f double prime?
0.
It's 0. So essentially, we're looking for where this graph equals 0. So if we look back over here again, all right, where does this graph equal 0? At 1, 4, and 7. Okay, do you guys see that? There's one issue though, and we didn't talk about this too much yesterday, so I really want to make sure to emphasize it today. One of those points is not a point of inflection, and I want to see if you guys can tell me which one and why. Why is 4 not a point of inflection? Good. It doesn't go across the x-axis. So because, like, if you look at this first one goes from negative to positive. All right? So that means that it changes concavity because it's changing from concave down to concave up. This one goes from concave up to concave down because it's changing from positive to negative. The middle one, however, goes from concave up to concave up because both sides of that are positive. So therefore, that is not an inflection point because it's still concave up on both. That middle one, it might be like an undefined point or it might be like a flat point of the graph or something, but it is not a point of inflection. So it doesn't actually change concavity. So that is why that's not a point of inflection. So our only two answers are points of inflection at x equals 1 and x equals, what did you guys say, 7? X equals 1 and x equals 7. You guys can write yourself a little note that says x equals 4 is not a point of inflection because it does not change concavity, because f does not change concavity. All right, last one on the back. Let's look at number 4. All right, so we're using this graph to answer the questions below. Let me zoom out a little bit so you guys can get them all on the same page. Here we go. All right, so it says use the graph below to answer the following questions. Notice that this is the graph of f prime of x. So this is the first derivative, kind of like the one we looked at yesterday. If you need to use your chart, but the better you can get at this from memory, obviously the better because the faster you'll get and you don't have to create the chart every time. So part A says, on what intervals is f increasing? So what is the derivative of f? Tell us about things that are increasing on the original.
It's positive above.
Good. So if f is positive, that means the original function is increasing. So if it's above the x-axis like it is here and like it is here. Really quick, I'm just going to add in a little 9, 10, 11, 12. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So f is increasing from what to what?
2 to 5.
2 to 5.
From 2 to 5.
And 8 to 12. Or infinity.
And from 8 to 12. And again, f was increasing because the derivative was positive. If f was decreasing, we would choose the other intervals where f prime was negative.
If it's like that on like a question, can we just put infinity? Or?
Yes, as long as, if it was free response, yeah. The fact that they don't have arrows on it supposedly means that it stops right there. But yeah, I would accept infinity as well. All right, for part B, at what values of x does f have a local maximum or a local minimum? So local maximums occur when f prime does what? When f changes from increasing to decreasing, there's a local maximum. What does that tell you about f prime?
When it goes from positive to
When it goes from positive to negative. Good. So I'm going to say local max at x equals, and then where does x change from positive to negative? At 5. Good. Is that the only place?
And
Okay. And then a local min where x changes from negative to positive. What are those two places?
2.
X equals 2 and x equals 8. Good. Part C, on what intervals of is f concave up or concave down? So remember, that's in the last 3 columns of the chart that we made yesterday. So it's concave up where f prime is what? Increasing. So where is f prime increasing? From 1 to 3 and 7 to 9 and 10 to 12. Good. So there are 3 intervals where it's increasing. So I'm going to say increasing, or actually this is concave up, huh? So concave up from 2 to 3, union 7 to 9, union 10 to 12. All right, so I want you guys to go back and figure out the intervals where it's decreasing, where it's concave down. All right, and last but not least, well, you should have gotten concave down from 1 to 2, 3 to 7, 9 to 10.
yeah,
I'm sorry, 0 to 1.
Instead of 1 to 2.
Thank you. And then I should have changed that from 1 to 3 for the first one. Let me change that. All right, so from 1 to 3 and from 0 to 1. All right, is that better? All right, last but not least, what are the x-coordinates of the inflection points of f? So remember, inflection points of f means the first derivative is a critical point, or in other words, a turning point. So where does this graph have turning points is essentially what it's asking. Say it again? Those are the zeros.
1, 3, 7, and 9.
There should be 1, 2, 3, 4, 5. Okay. So x equals 1, x equals 3, x equals 7. No, 1, 2, 9,
Oh,
and
10.
10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, good. So 1, 3, 7, 9, and 10. Good. So that's all the notes for today.